So in previous videos, I've made a big deal about how it's important to memorize this formula here in the middle. And whenever I was a student and I saw this for the first time, I did think it was just a little bit magical how the dot product gives you, the angle between the vectors. And we also talked before about how the angle between the vectors doesn't really care about the length of the vectors. And so it sort of shows up in this formula that if you take the dot product of the normalized vectors, it's the same thing. So all of that is already discussed. But what I would like to do now is sort of show you what is the proof of this? How do we know for sure that this formula really does give us that theta, that angle between these two vectors? So I'm going to start off by, moving from, or beginning with this picture I have over here of my vector u and my vector v. And what I want to show you is that vector addition works like this. If I just slide this vector v over so that this v is now situated tip to tail with the vector u, then the corresponding vector from the tail of u stretching all the way to the tip of v, this vector would be u plus v. Okay? Now let me make another picture for you. Here's my vector u. I'll try to draw it the same way. And now if I draw my vector v like this, and I line them up so that the tip of v is touching the tip of u like this, it's like I did it tip to tail, the same way we added the vectors, except I've kind of done it in the opposite direction, right? And so what's the opposite thing of adding two vectors? Well, the opposite of adding is subtracting, right? And so this resulting vector is going to be the vector u minus v. I hope that makes sense. And this is where we're going to begin. So again, let me just draw this picture one more time for you of my vector u and my vector v, just like we had before. And of course the angle between them, I call this theta. And now I can actually complete this triangle perfectly by drawing this vector, and this is the vector u minus v from over here. So now I have a triangle, and since I have a triangle, I can use what we call the law of cosines. And what the law of cosines says is that if you have some triangle, let's label this triangle side lengths A, B, and C, and the angle across from side C is going to be my angle gamma. What the law of cosine says is that c squared is equal to a squared plus b squared minus 2ab cosine gamma. So in the case where gamma is a 90-degree angle, or gamma is a right angle, that would make this a right triangle, where c would be your hypotenuse. And of course, cosine of 90 degrees, or cosine of pi over 2, is 0, so this term would go away, and we would be left with c squared equals a squared plus b squared, and that would make the Pythagorean theorem. So you could say that the law of cosines is a generalization of the Pythagorean theorem, or you could say that the Pythagorean theorem is just a specific case of the law of cosines. But now let's apply this to our triangle over here with my vectors u and v as two of the sides, and of course the third side, like I showed you, is the vector u minus v. In this case, the length of this side is going to be the norm of u minus v. And then, of course, I will want to square that. Here, I have to pick one of my sides to be a. Let's call that u. And so the side length there would be the norm of u. And then, of course, the last side I have to pick is going to be my v side. So b squared is going to be the norm of v squared. And then minus 2 norm of u norm of v cosine of theta now. Okay, so hopefully this all makes sense, how I went from the law of cosines and then applied it to this triangle we have and got the expression we have right here. Now we're going to use some properties of the dot product. Namely that if I have, u minus v, and then I take the norm of u minus v, that norm is going to be basically the square root of u minus v dot u minus v. And then whenever I square this, that's going to cancel with the square root. I'm going to be left with this. Okay? Now here, where I have the norm of u squared, I can do the same thing. This is going to be u dot u, take the square root, and then square it. Well, the square root and the square cancel, and that goes away. So I have u dot u, plus same thing happens for v, so I have v dot v, minus 2 times the norm of u, leave that alone for now, times the norm of v, times cosine of theta. Now, let's expand out this dot product right here. And, the dot product has this distributive property where I can go ahead and write this as u dot u, looking at the first two terms, and then the outer terms are going to make minus u dot v, the inner terms are going to be minus v dot u, and then the last term is going to be plus v dot v. Now I'm going to move these two terms over to the left side of my equation, so I have minus u dot u minus v dot v equals negative 2 norm of u, norm of v, cosine theta. Okay? So I see some things that are going to cancel. I have plus v dot v and then minus v dot v, so that goes away. I have a positive u dot u over here and a minus u dot u over here. And so what will we be left with? We're going to have minus u dot v minus v dot u, but of course the dot product is commutative, and so I can write this like so. This is going to be equal to, let me go ahead and divide both sides of my equation by negative 2 norm of u, norm of v. So this will be equal to cosine theta on the right side. Okay? Now, hopefully you are seeing how this is shaping up. In the numerator, I just have negative 2 times u dot v, right? Write that over here. In the numerator, I have negative 2 times u dot v. And so that negative 2 is going to cancel with the negative 2 in the denominator. And so putting this all together, canceling out the negative 2's in top and bottom, gives me that cosine theta is equal to u dot v over norm of u, norm of v. And so that is the proof that the formula relating the angle between two vectors with the dot product of those vectors works. We know it has to be true. Now, you recognize then that this whole proof really relies on the law of cosines. Like, we got started by just stating the law of cosines and then applying it to this particular triangle. And so if this law of cosines weren't true, then this whole formula would not be true. And I personally haven't seen the law of cosines presented since I was in 10th grade geometry. And so maybe it's good to just review what, why do we know that this law of cosines is true? Where did that even come about? So I left space where we can talk about the law of cosines here and also present a proof of the law of cosines. And I'm going to begin by drawing myself a triangle, and it's not a right triangle. This is just any triangle. Let me go ahead and label it like this, sides A, B, and C. And so normally, I like to label the angle across from side A, the angle alpha, the angle across from side B beta, and so this angle across from side C is going to be gamma. So those are just the Greek letters corresponding to A, B, and C. I actually don't care about these angles though for right now. Then I'm going to draw what we call an altitude of the triangle. What makes this an altitude is that it makes a 90-degree angle with this side B, and I'm going to label it H. The last thing I'm going to do is I'm going to label the side of this right triangle over here, side length D, and so remember this B side length is the total side length across the bottom, but lowercase d is just the side length of the smaller right triangle here. Okay, this is the setup. Now we should recognize a few things, namely that in the right triangle on the left, I can use the Pythagorean theorem, which would tell me that a squared is going to be equal to d squared plus h squared. Okay? Now, what would d be? How do I find the length of d? D is just going to be a times cosine of gamma, right? Because cosine of an angle is just the ratio of the adjacent side to the hypotenuse, and so that's how we come up with this equation here. Now, what about the side length c? I can use the Pythagorean theorem here to state that c squared is going to be equal to h squared plus, well, what is this side length of the right triangle on the right side? That's going to be length of b minus d all squared. All right. Now, what would h squared be? I can go back to my first equation and find that h squared is just going to be a squared minus d squared. Do we see how we got that from my first equation up here? And then this, if I expand it out, is going to be plus b squared minus 2bd plus d squared. I see some d squareds are going to cancel because I have minus d squared and plus d squared. And things, believe it or not, are beginning to shape up for us. Now I have c squared is equal to a squared plus b squared minus 2b times d. And now I have to go back and look at what is my definition of this d right here. And since d is just a times cosine gamma, I can drop in my a times cosine gamma right here, and voila, we have the law of cosines. So hopefully that's a little bit more satisfying than just being given the law of cosines. The last thing I'm going to do in this quick little proof video is address the proof of this formula I gave for finding a projection using the dot product. Okay, so we talked about how the projection of u onto v goes like this. Right? Here's my vector u. Here's another vector v. And so the projection of u onto v means that I find the component of my vector u that happens to be parallel to v. So that would look like this green vector I'm drawing on top here. Of course, it's parallel to v, but it's just the component of u that's in the direction of v. And so this is what we call the projection of u onto v. So how do I find the length of this vector? Well, the length of this vector is going to be cosine of theta. Remember, cosine of theta is the ratio of the length of the adjacent side to this angle theta to the hypotenuse, which is going to be the magnitude of this u vector. And notice this makes a little right triangle here when I'm talking about the components. And so the magnitude of u, of course, is then going to be the norm of my u vector. So this is giving me the length or the magnitude of the projection of u onto v. And so that's where this scalar comes from. This is, of course, a scalar. So there's the magnitude of this vector. What about the direction? Well, this right here, you'll notice, is the vector v, but it's normalized. And since this is normalized, it is a unit vector, meaning it doesn't change the magnitude, because the magnitude of this unit vector is 1. But it does give us direction, since this is a vector. And so I have the correct magnitude given here, and then the correct direction, that is the direction in the direction of the vector v, given there. Okay? Well, if we move on from this formula, what I can do is say that this, norm of u times cosine theta, there is a formula that we've talked about just in this video where I said that cosine theta is equal to u dot v over norm of u, norm of v. If I take this formula and I multiply both sides times norm of u, then norm of u cosine theta, you'll recognize from over here, must be equal to u dot v over norm of v. And then it's just a quick little, properties of the dot product thing to say that this is the same thing as u dot v norm of v, which is what I have in these parentheses over here. Okay? Now, finally, to get to our formula for this projection, all I have to recognize is that if I move this inside the parentheses, well, norm of v times the norm of v is just the norm of v squared, and it's a property of the dot product that this is just v dot v. Okay? And so that is how I end up with this v dot v in the denominator here, and that is how we end up with this formula for the projection of the vector u onto v.